Okay, if no questions, then we'll take a look at some of the problems here. 92, a mixture of iron 3 oxide and iron 2 oxide was analyzed and found to be 72.0% iron by mass. So this is a mixture problem. Iron 3 oxide will have some percentage iron, and iron 2 oxide will have another percentage iron. You know, can you tell which one has a higher percentage iron just by looking at it? Is it going to be iron 2 or iron 3? It's kind of hard to tell, you know. So what you have to do is you have to normalize it. And so one way of normalizing it is by making it one iron, so or doubling it. And so there are two. So we got to keep one of these the same, and then it's easier to compare. So for example, if we doubled the iron here, it would be Fe2O2. This is Fe2O3. This one has more oxygen. If it has more oxygen, it's going to have a lower percentage iron. This one's going to have less oxygen, Fe2O2, that will have a higher percentage iron. You see how you can do that? So these are little tricks you use in multiple choice, because oftentimes a multiple choice question will ask you which one has the highest percentage, let's say iron, out of these. And if you can do that, then it saves you calculation versus having to calculate it. And so actually, this is kind of a favorite multiple choice type question, not of me, but of standardized tests. I've seen it many times. And so once you know, okay, which one has a higher, then you know it's going to be bordered between there. So this one's higher, this one's lower, and we can do it graphically. You know, it's going to be bordered. 72% might be somewhere in between the two. And so this is just a mixture problem. So before. Okay, after 92, we'll take a look at 94, I think is next. Just a few words. I mean, if you want me to solve or work these out, I can. Maybe not all of them. A few. Write chemical equations to represent the following reactions. Calcium phosphate is heated with silicon dioxide and carbon, producing calcium silicate. This silicate is normally SiO4. Here it's SiO3 with a 2- charge. And silicate, they have different formulas that you're going to see, you know, depending on, because the geology of these is pretty interesting. The compound. So let's take a look. One thing you don't want to do, though, is rely on Google or whatever to figure things out, because some of these are just wrong. I think here they have SiO4 2-.
Isn't it just SiO4?
No.
4-.
It would be, if it's going to be SiO4, it's going to be 4-. But there's something called SiO2, which is coarser silica. It's SiO4 4-. You have to be careful, because then you have SiO2 3-, Si2 6, 7, -7.
That's impossible.
We have to see what the structure of that looks like. But there could be like things that are like disilicates or trisilicates or cage structures. You can have a lot of different things, because silicon is like carbon. What's special about carbon? It can form 4 bonds. And so the chemistry of silica it's not to the same extent, as carbon. There are a lot of analogous compounds to carbon-containing compounds. Like we used to buy oil all the time, but it wasn't like a normal oil. Most oils are based on carbon-carbon, hydrocarbon type structures. But these are silicon, and so these were silicon-based oils. They're very expensive, but they were good at keeping water out, and they were good at temperature, withstanding high temperatures. go back to this. So, you know, it's not necessarily wrong, let's say. It's just how we watch nomenclature. P4 is white phosphorus and carbon monoxide. And so this is one of those things. This is like a skeleton redox. You know, we don't have to figure out what the products are. They just mix it together and see what happens. And sometimes we get a combination of reactions. We'll get redox, acid base. So, and sometimes we'll break it down into individual steps. Copper metal reacts with gaseous oxygen, carbon dioxide, and water to form green basic carbonate. So this is mixed anion salt. And so we have a carbonate and two hydroxides, forming a crystal lattice. When we have something like this, the nomenclature becomes quite difficult at times. A reaction responsible for the formation of the green patina or coating, often seen in outdoor bronze statues. So this is the green stuff. They call it basic copper carbonate. Copper 1 or copper 2? Well, carbonate is -2, and 2 hydroxide is going to be -2. So altogether, we're going to have -4. And so it's got to be copper plus 2. Yeah. All right, so mixed species like this happens. This is a metathesis, you know, when we have this. But overall, it's a redox. You know, copper is being oxidized. And then we're going to have carbon dioxide going to carbonate, and you're going to have some water converting it to hydroxide. C, white phosphorus and oxygen gas will react to form tetraphosphorus decoxide. This is just an element plus element combination. So if we were to burn phosphorus completely, what would it burn to? And so there are different forms of phosphorus. These are allotropes. And so let's talk about this one. You should have been able to predict if we had the complete combustion of white phosphorus. Anyway, if you burn phosphorus completely, what's the max oxidation state? Let me grab a pen. Perfect. So here we're going to assume complete oxidation. And this is going to form, okay, if phosphorus is in the 5, now I'm not going to write +5, I'll just write Roman numeral 5 because it's very high charge, hard to stabilize. And oxygen is in 2-. Let's see, what would the ratio be? P2O5. Now, P2O5 forms these molecules, and that's actually the empirical formula for the molecule. These molecules are actually these kind of large cage-like structures. I'll show you what it looks like. And so that's the empirical form, but you know, that's what we know, the empirical formula for such things. And so this is, P2O5 is only half the molecule. The full molecule is double that. And so the molecular formula for this is P4O10. Okay, so this is the empirical formula. What we would have predicted is the empirical formula because we don't know what the molecular formula is unless we have what additional information. What would we need to have known to be able to predict the molecular formula? Yeah, and so we would have had to weigh the molecules, either with a mass spectrometer or do it some other way. So this one we should have been able to predict at least the empirical formula, maybe not the molecular formula. Actually, definitely not the molecular formula. Now, they're saying that the P4O10 reacts with water. Plus H2O. P4O10 reacts with water to form, in this case, phosphoric acid. What kind of reaction is this? Is this a redox reaction or acid? acid-base or metathesis reaction? What kind of reaction is that?
I don't know whether it's single replacement or acid base.
Well, single replacement has to follow the format A plus BX. And since A's got to be an element, and so this is actually not an A. This might be a double replacement. Sometimes people do double replacements with molecular compounds and with water by going HOH, like this. And so this would be my AB plus CD. This happens sometimes. So for example, one of the most common, this is the way I used to do it for sodium metal. Sodium metal and water, I treated this as a single replacement, so it would be sodium plus HOH. And what this would form is sodium hydroxide plus hydrogen. Yes. And so this is my A plus BX yields AX plus B. And so that works sometimes, where we can treat a molecular compound like an ionic compound, but you know, this is not that type. It might be a redox reaction. And so I wouldn't necessarily call this metathesis or double replacement or single replacement, but is it a redox reaction? No.
Oxidation state changes.
Did the oxidation state change? What is it over here?
+5.
+5. Oxygen is -2 here, -2 here. What is it, phosphorus here? +5. Oxidation state didn't change. You know what kind of reaction this is? This is a Lewis acid-base reaction. In Chem 4, you're supposed to memorize this. I didn't have my students memorize it, but maybe your instructor made you memorize it, and that is non-metal oxides, this is non-metal oxide, plus water makes acids. Did anybody have to memorize that? Non-metal oxide plus water makes acid. Metal oxides plus water makes metal hydroxides or bases. Semi-metal oxides plus water makes amphoteric species. Semi-metals plus water makes amphoteric species. So those are examples of Lewis acid-base reactions. And so let's take a look at a couple of Lewis acid-base reactions that are quite common. The first Lewis acid-base reaction I'd like to do is a non-metal oxide, CO2 plus water. Yields what? All right, so we have CO2 and water, and when we do Lewis acid-base reactions, we have to have the Lewis structure. Well, I haven't gotten to Lewis structures, but I assume you've done Lewis structures in intro chem, correct? And so we can draw out the Lewis structure for CO2. Looks like that. And then for Lewis acid-base, we want to look for formal charges first. But are there any formal charges in CO2? There are no formal charges. Okay, if there are no formal charges, then the next thing we look for are delta pluses and delta minuses. Are there any delta pluses and delta minuses in CO2?
So you have to see that.
Yeah, because oxygen's more electronegative. It's going to pull the electron cloud towards it, and it's going to make... It's nonpolar because they cancel out, but even though it's nonpolar, it's still there.
Yeah.
And therefore, what we have is this. This is a base site. This is an acid site. This is a base site. Base sites are going to have negative charge density and lone pair. Acid sites will have positive charge density. Okay, then we have water. Water is amphoteric. Water can go either way. So when we look at water, water, this is base here for water. This is acid for water. There are no formal charges there. It all depends. Okay, so what do you think is going to happen? Well, you know, chemistry is electrical interactions. So what can happen is the base site on water can attack the acid site, or the base site on CO2 can attack this. So we have two possibilities. Oh, here's your. So possibility one, this comes in here and attacks this carbon here. But carbon's already got an octet. Do you see that? And so if that happens, then it's got to kick some electrons out. Otherwise, carbon can't have more than an octet. And so what's going to happen is it's going to kick these. So this would be like 1, this would be 2. 2. The other possibility is this. The base site on CO2 attacks the acid site in water. So this is A, and then this is going to be B. So basically it's just going to pluck a proton off water and make hydroxide. And so we have two possible, what we call mechanisms here. We could have the 1-2 or the AB. We try them both and see which one might lead to something, you know. It turns out the AB kind of is a dead end. If we took the AB route, it eventually kind of dead ends. So instead we'll take the 1-2 route. If we take the 1-2 route, then we can get somewhere with the 1-2 route. And so that's what we're going to do. We'll take the 1-2 route. And those are the only two possibilities. Do you see that? There are no other possibilities here. So when we do Lewis acid-base reactions, it's always the base attacking the acid. And so in this case, we're going to call water the base, and CO2 is the acid. Versus in the other scenario, it was flipped. CO2 was the base and water was the acid. And so here, the base is going to attack the acid, which would be the carbon here, which is a positive charge. And there's going to be too many electrons around here, so we've got to lose one bonding pair. And so what we end up with is this structure that looks like this. Yeah. Here. When you look at this structure, is the octet rule okay? I got to make sure I didn't exceed an octet. Right. Is the octet rule okay? Yeah, the octet rule is fine. So does this structure look good to you, or does it look off? Like something's not quite right? When you look at this structure, does it look a little off to you, or does it look good? In other words, is that all you look at when you analyze Lewis structures? Do you just look at the octet rule, or do you look at a little bit more than just the octet rule? Well, electronegativities haven't really changed much. I mean, we have oxygen's electronegative and carbon. It's not the electronegative, it's something kind of related.
Formal charge?
The formal charge. You know, when we look at Lewis structures, what are the formal charges in CO2? 0. And what are the formal charges in water? 0. But what are the formal charges in that structure? There. So when we look at this, we look at this oxygen. What's the formal charge in this oxygen? Remember, formal charge is 50-50 split or winner take all? 50-50 split of the bonding, so count the electrons, 1, 2, 3, 4, 5, 6, 7. How many electrons is oxygen supposed to have?
6.
So it has an extra electron. Extra electron is negative. How about this carbon?
0.
0. We don't write 0 for formal charges that are 0. What about this oxygen? 0. This oxygen? Plus 1. These hydrogens? 0. And so what's screwed up about this is the formal charge. One oxygen ends up ahead by 1 electron, one oxygen ends up behind by 1 electron. And they're both oxygens, they both are highly electronegative. And so this isn't stable, right? And so what can happen is it can revert back to CO2 and water. Just decompose here. Or this. What's more electronegative? A neutral oxygen or an oxygen with a positive charge? Which one wants electrons more?
The positive.
Yeah, and so this oxygen has electronegativity of 3.5 according to Pauling's electronegativity scale. This oxygen would have an electronegativity that's even higher than 3.5. Probably not, I don't think it's like fluorine, maybe, I'm not sure, but it's going to be higher. And if it's higher, what's it going to do? It's going to suck in the electron cloud towards it and make the hydrogen much more, not negative, much more positive, which makes it much more acidic. This is why hydronium is so acidic. If you think, why is hydronium so acidic? Hydronium is so acidic because you might think, hey, this is just like water. And so shouldn't this have the same acidity as water? No, this doesn't have the same acidity as water. This is much more acidic than water. Why? Because of the much larger positive charge it's going to generate on the hydrogen because of this oxygen sucking electron cloud from this. Versus this, you know. And so this is not nearly as acidic. Do you know the difference between inter and intra? Inter versus intra. What's the difference between inter and intra? Like interaction. Interaction is usually between two different species, like an acid and base. There's going to be interaction between the acid and base, acid. But what about intra? Is there something called intra-action? Intra. Yeah, within the molecule itself. And so what we're going to have is this. Do you see this oxygen here? Versus this oxygen. Which oxygen do you think is more basic? Which oxygen do you think wants a hydrogen more? The one with the negative charge. And do you know that single bonds can freely rotate? So this is kind of like, this part can rotate around, spin around like this. And double bonds cannot freely rotate, it turns out. We'll talk about that in this chemistry class. So what I'm going to do is I'm going to rotate this hydrogen, and in fact normally the hydrogen is rotating. I'm going to rotate it over on this side. So let me just do that here. So this is kind of the same thing. I just want to rotate this like this. It's actually not correct. I don't have to rotate it because of resonance. You know, there's resonance formed here. And so both these oxygens are actually equal. And the bond here is what we call 1.5 bond. And the formal charge on each oxygen is the same at -1/2. But I'm not going to do that. I'm just going to write it over here like this. And so we're just looking at one resonance form here, although it doesn't interchange. You know, the resonance hybrid is incorrect. But for Lewis acid base, it's easier to analyze this way. Do you know what? What's going to happen is this hydrogen is very acidic. And this oxygen is very basic. You know, so this oxygen is like hydroxide. Is hydroxide a good base?
No.
No? Yes? Yes, okay. Yes, I need it. You keep me on my toes, right? But anyway, this one here is vibrating like this, right? And so what's going to happen is this lone pair is going to get pushed into this s orbital and kick these electrons out like that. And so in other words, this is called an intramolecular proton transfer, in which the proton gets pulled off by another atom within the molecule. So intramolecular proton transfer. Okay, when we have this intramolecular proton transfer, what do we end up with? Well, we're going to end up with this. Okay, what are the formal charges in this molecule here?
Let's see.
All of them are 0.
Yeah.
Do we have octets?
Yes.
Yeah, absolutely.
Yeah. So this one looks good. Do you know the name of this?
No carbon.
This one's called H2CO3. H2CO3 is
Bicarbonate.
carbonic acid. This is carbonic acid. And so CO2 and water can react to form carbonic acid. The carbonic acid is not as stable. And so if we had carbonic acid, it much prefers to decompose into CO2 and water. CO2 is more energetically favorable. But that doesn't mean some carbonic acid can't form, because there's going to be a small population in the Maxwell-Boltzmann distribution that can make it up to form carbonic acid. And so there'll be a little bit of carbonic acid. It doesn't decompose 100%. There'll always be a little bit of carbonic acid because of the population here. So we have these things like, for example, carbonic acid decomposes into CO2 and water. Sulfurous acid decomposes into SO2 and water, and we can go back and forth in terms of that. SO2 and water make sulfurous acid, and so SO2 plus water makes sulfurous acid, H2SO3. SO3 and water makes what? Sulfuric acid. And so in Lewis acid-base reactions, we have to draw out the Lewis structures and then work out, which atoms interact with which atoms, acid-base. Okay, so those are our non-metal oxides. The next one are the metal oxides. Metal oxides like calcium oxide. Calcium oxide solid plus water makes, do you know what it makes? Calcium hydroxide. So this is a Lewis acid-base reaction. Calcium hydroxide turns out to be soluble. Calcium oxide is insoluble. And so when we look at it, calcium is a Lewis structure. It's an ionic compound. So what we do is we draw out the ions like this and make a lattice. But in calcium oxide, it just extends out in 3 dimensions. So we end up making a 3-dimensional lattice of calcium ions and oxide ions, which would be similar to sodium chloride. But this is quite a bit different than something like sodium chloride because of the charge on the ions. These are 2 plus and 2 minus. So it's a very strong lattice. It's going to have a high melting point. Oxide turns out to be a powerful base, but it's kind of stuck in the lattice here. And so what we have to have is we have to have a water molecule come in here. And so the water molecule comes in and collides. And so if the water comes close enough to the oxide can pluck the hydrogen off the water. This is kind of like a Bronsted acid-base reaction. And then if it plucks the hydrogen off, it's going to leave the electrons because it just plucks the proton, the H plus off, leaving the electrons behind. And so what we end up with here is we're going to convert this oxide into a hydroxide. There's a negative formal charge on there. And we're going to convert the water into a hydroxide here. Formal charge, etc. And so what we end up doing is we convert calcium oxide into calcium hydroxide. 2 hydroxides for every calcium. And so this is an example, again, of Lewis acid base. Lewis acid base is not so easy like Bronsted, so this is why we focus on Bronsted. Because with Lewis acid base reactions, there are other factors too. I mean, there's just a wider variety of Lewis acid base reactions. The wider variety is it's something like this, BF3. You might have learned in Chem 4 that BF3 is an exception to the octet rule. And it has a structure like this. We can make it have an octet if we double bonded fluorine, but is fluorine willing to double bond?
No.
No.
Yeah, many bonds as it wants.
I'm sorry?
I will say it can have many bonds as it wants.
As many bonds as it wants?
I wouldn't. Yeah.
Actually, it doesn't want. It doesn't want. You know, as many bonds as it wants is just one bond. That's as many bonds as it wants. Because if it forms 2 bonds, like here, what's the problem with forming 2 bonds like this for fluorine?
It gets a little bit too much.
Well, that means it has to share with boron, and fluorine doesn't like to share. You know, if we take a lone pair, the lone pair need not be shared with anybody. This lone pair belongs entirely to that fluorine. It's not being shared with anything except, you know, vacuum, space. But when we put that lone pair into a bond here, now all of a sudden it's sharing it. You know, it's not perfectly covalent. That is, it's not perfectly 50-50 sharing, but it's losing some. If we assume it's perfectly covalent and look at the formal charge, what's the formal charge of this fluorine here?
Negative. Oh, sorry, positive.
Positive. And the formal charge of this boron?
Negative.
Negative. And so essentially what we're saying is that fluorine's going to give an electron to boron. Will it?
No.
Not likely.
No, because of the huge difference in electronegativity. And so it's not going to happen. What happens is this makes this a powerful Lewis acid. And so this is a very strong Lewis acid. This has got less than an octet. And so we could have a Lewis base like ammonia come along. Or, yeah, just have this. Here, the nitrogen delta minus, and it's going to attack this boron. Okay. Well, we don't have to kick any electrons out because we don't even have an octet there. And so what we form is something called a Lewis acid-base adduct. Like that. Although we're going to have formal charges here. Now the boron is going to be 1, 2, 3. This is going to be a negative formal charge on here. And the nitrogen is going to have a positive formal charge. Well, fluorine won't share electrons, but nitrogen will. And so we have an ammonium style derivative on the end here. And we have this in this scenario. And so this is a Lewis acid-base reaction. So boron trifluoride is a very powerful Lewis acid. It will react with a lot of bases. So it's quite reactive. Okay. And there are other examples. So I'll skip. All right, that was 94. 97. Let's take a look at that. Yeah. So something like this, you know, how do you study something like this? Study something like this is you just either look at it every day or you write it, you know, see if you can do these mechanisms from scratch, you know. Is it possible? It's like if you have a recipe, you know, can you do the recipe from memory? Or do you have to read the recipe? The same thing with problems. You know, we do problems in class. You should make sure, like, I might have mentioned this before, like if the instructor ever put a problem that they did in lecture, I thought those were free points. Those were super easy points because I had every single problem that was done in lecture kind of memorized. And you think, oh, memorization, that's not learning. But it is learning in a sense. So I had every single problem memorized. But it memorized to the extent that if they threw in twists into the problem and made it a little different or a little trickier, I could figure it out or try to, you know. Figure it out. And so you want to do the same thing. You want to make sure that you understand it. There's a story. When I was at UCSB as a graduate student, one of the professors there, who's a theoretical chemist, and he was actually a good friend of mine too, but he was telling me about his class. He was teaching a class there, and it was all chemistry graduate students. And he said he went through, he's a quantum mechanics guy too, he went through a calculation that took 3 days. After the 3 days, he asked, the class was only 9 students, he asked the class, okay, do you guys understand all the steps, right? And everybody said yes, they understood it. It seemed very clear when he presented it on the board, and he went through every step in detail. And then he said, okay, the next day he decided to give a quiz. It was the exact same problem, and the results surprised him because nobody got the answer. And he just did it. And then he was perplexed because he's thinking, why didn't anybody get the answer? I mean, they said if they didn't understand, they should have said something. But they thought they understood it, right? You think you understand it because it seems to make sense when somebody's telling you how to do it. But when you actually have to do it yourself, then it's a different story. And so that was the moral of the story is to, you know, you got to actually sit down and try it from scratch to see, do you really understand it? Or you don't even have to really understand. Some people get so hung up. You know, it doesn't make sense. I don't understand it. If you don't understand it, just memorize it. You know, because that's the first step in trying to gain an understanding. Because if you give up at that point, then there's no use in kind of coming up and understanding. And eventually what happens is, okay, it doesn't quite make sense, but down the road, then everything clicks. You know, some subconscious thing works out, and it just it makes sense. You know, maybe some things will never make sense, but you know, a lot of things will eventually with time. Because your body, yeah, I mean, your brain maybe, you know, that's left hanging, and it's left hanging. Your brain doesn't like it, and your brain's going to try to figure out what's going on. That's good. Hopefully, in enough time for the final exam. Anyway, that's some study advice. Make sure you can do all the problems we do in class. And, the concepts. If you don't understand any of the concepts, ask. You know, we can cover those again, or check. You know, other things I did was I looked in other books. You know, because other books will have a different author, and different authors will present things differently. It's always useful. 97, hydrogen gas is passed over iron 3 oxide at 400 degrees C. Water vapor is formed together with black residue, a compound consisting of 72.3% iron and 27.7% oxygen. We have, you know, we have the, you know, what you could call the original oxidizer. You know, what is the, when you think of oxidizer, what is the oxidizer that everybody thinks about? Oxygen. And so, it's so much so that we have a symbol for oxidation. You know, the symbol for oxidation is this. This means oxidize. Some oxidizer. And so, I guess the prototypical oxidizer is oxygen. What about the reducer? Is there some reducer that's like, you know, the prototypical reducer?
Hydrogen.
Hydrogen is it. And so this is the generic symbol. It doesn't have to be oxygen. It could be any oxidizer. We just give it the symbol O here. And the same thing with the reducer. This is like the generic symbol. This is a reducer here. Hydrogen is a great reducer, though. And so what we're having is partial reduction. Remember we talked about complete oxidation? Well, we can go backwards here. If we completely oxidize iron, well, actually we don't form Fe2O3, do we? Yeah, we do. Fe2O3, because iron 3 is about as high as you get. Iron 4, you know, iron 4 is a bit too high in charge for such a small atom as iron. And so iron 4 turns out to be quite unstable. When I was a student at UCLA, I was trying to make iron 4. You know, I was trying to make iron 4. So if you try to make iron 4, you need what? A very powerful oxidizer to make it. And so the powerful oxidizer I was using was fluorine. But fluorine's a gas. Gases are mostly empty space. So I didn't want a lot of empty space. So you know what I did to the fluorine gas?
Liquefied it.
I liquefied it. After I liquefied it, I captured it, and then, well, liquid fluorine is so cold, and cold fluorine moves slowly. So you know what I did after I liquefied it? Heated it up. And so I was using hot liquid fluorine to make this.
Brought it to a simmer.
Yeah. And then, you know, I always worry about the fluorine chemist handshake. Did I show you the fluorine chemist handshake? Probably. Yeah. Anytime. This is what I was taught, the fluorine chemist handshake. You know.
Did you end up making iron food?
I think I did, because it wasn't the first, because I was trying to repeat somebody else's experiment who had claimed they had made iron 4, so I wanted to repeat that to see if I could make it. And so it wasn't anything new. But the problem I had was the tube I was using, which was made out of Monel, which is kind of like stainless steel. It's super corrosion resistant steel. The lid on that was like welded shut. And this I had to do in an air-free environment because, you know, in air there's water, and water can kill off iron 4 instantly. There's water, I mean, iron 4 will oxidize water in an instant, basically. So it was in an air-free environment, and so I brought some wrenches in there, and I was trying to break the lid free. It was screwed on there, and I couldn't. It was too hard. So I brought in a sledgehammer in this giant box. This box. I'll show you what it looked like.
If it was welded shut, could you drill into it?
I don't think so. Let's see if there's some images of the. This is what it looks like here.
glove box.
Look, it was just like this. This is it. The gloves are sticking out because you have a high pressure, not super high pressure, but high pressure. This glove box is filled with argon gas. This is called the Anki chamber here because you don't want any air or moisture to get in there. And so what you do is you put your sample in here and then suck out all the air. There's all vacuum stuff here. And then you backfill it with argon and then suck it out again, backfill it, suck it out again, backfill it. So eventually there's no air. This is like rinsing, rinsing your burette with the acid or with the base, this kind of pipettes. And then you bring it in there. So I brought wrenches in there, I brought a sledgehammer, I brought a bunch of tools inside there, and I couldn't break it loose. So I was getting frustrated because it just wouldn't break loose. So then I took it down into the machine shop so I could put it in a vise and then hammer it loose. I just wanted to break it loose just a little bit, so that I can go back into the dry box and then unscrew the lid. But what happened was I broke it off, like it just, when it broke free, it just broke free and the lid fell off. And then I looked inside there and it was green. Well, the iron 4 compound was supposed to be green, but then it just went and went to rust, basically, after that. It just didn't survive, unfortunately. And then I ran out of time. That's the problem, is you run out of time in research. And there's no more time, and then there's my time to leave UCLA. But that was one thing that was left hanging. I wanted to finish, but I didn't. It was so close, I thought. I thought I had it. But like everything, and that's what science is. You don't want to. You have to stop at some point, and if you want to complete everything, it could take you, more than your lifetime to complete. That's what we do. Well, anyway, I'll tell you about the fluorine chemist handshake later, but basically what we're going to do is we're going to reduce this. This is the opposite of oxidizing. So what we could reduce it is, we could reduce it to iron 2 oxide, or we could reduce it all the way to what?
Magnetite? F304.
Oh, well, magnetite's in between, that'd be 304s. In magnetite, we would have only taken one of the iron 3s and reduced it to iron 2.
Oh, could we reduce it all the way down to iron?
We could reduce it all the way down to iron. And so, if they would have just kept at it, they could have reduced this all the way down to iron. So if I was thinking I'm passing hydrogen over Fe2O3, I'm thinking I'm going to reduce this all the way to iron metal, but they didn't. They reduced it to some compound consisting of iron and oxygen. You know what I think that compound is?
What?
Iron 2 oxide. That's what I think it is. But it's possible it is magnetite. Maybe it's partial reduction. Well, this is all partial reduction. But in this particular case, this is kind of a chapter 3 type thing where you figure out the empirical formula. But one of the good things about Wikipedia and the CRC is we can just get the percent. Like, for example, I think Wikipedia does this. Give us the percent composition by mass. Does it? Well, it doesn't. CRC does. The CRC gives us the percent composition by mass. And so it's pretty easy to see. But we could figure it out quite quickly. Oxygen is 16. The molar mass of this is 71,844. So we'll just do 16 divided by.
Should be 55.844 if we do exactly 16.
Yeah, we're going to do exactly 16 by 71.844.
Yeah, 55.844.
55?
Yeah.
It should be less than that. Oh, not minus 16, sorry. 16 divided by 71.
Oh.
22% oxygen. If it's 22% oxygen, then the rest is iron, so it's got to be 77.7% iron. Let's see what they got. Oh, that's off. This is 72% iron. So it could be magnetite or something like that. But anyway, this is just trying it and seeing what happens. You know, trying it and seeing what happens. So examples of oxidation in we've looked at before. For example, this. What is this?
Alcohol.
Yeah, which alcohol?
Butane. No. Bute's for it.
Ethanol, 2 carbons. If we oxidize this completely, what does it form? Complete oxidation forms.
CH3, CH2H. Or each CH3, CH2.
No, not that. Complete oxidation of ethanol forms what? So if I burn ethanol, what does it burn to?
C.
CO2. Does it go beyond CO2? No, that's the limit there. But it depends on the conditions. You know, the conditions are going to dictate how it burns. So for example, here, in this case, let's say a tiny bit of air gets into your wine bottle. It might not be oxidized to CO2, it might be partially oxidized. And so as far as partial oxidation goes, we could partially oxidize this to this compound, which is CH3CHO. CH3CHO looks like this. It's going to have a CH3, and it's going to be bonded to a C double bond, like this, and an H like that. Do you know what that's called?
Acetate?
Well, this is called acetaldehyde, or this is an aldehyde. This is an aldehyde. Or it could be further oxidized to CH3COOH. It would be acetic acid, etc. And so it depends on the conditions. You know, we could have partial oxidation, complete oxidation. And so it gets tricky to predict. And so sometimes you just try it and see what happens. If otherwise, we just predict complete oxidation or complete reduction. You know, I would have predicted complete reduction. So if I'm going to reduce iron 3 oxide, I would have taken it all the way to iron. You know, just like if I'm going to oxidize iron, I'm going to just predict complete oxidation. I'm going to take it all the way to rust. You know, it's easier, and not necessarily wrong. 103. What is the molarity of sodium chloride if the solution has 1.52 ppm sodium? Assume that sodium chloride is the only source of sodium. For every mole of sodium, we have 1 mole of sodium chloride. And that the solution density is 1.00 grams per milliliter. So this is just dimensional analysis, unit conversion. So we're going to go from grams of sodium to moles of sodium to moles of sodium chloride, and stop. And then on the bottom, we're going to have 1,000,000 grams of solution. So we'll go from 1,000,000 grams of solution to milliliters of solution, and from milliliters of solution to liters of solution on the bottom, and then we're done. And that's going to give us molarity. So this is not really an advanced problem. This is just chapter 3. I guess what it makes it an advanced problem is it's ppm. 110. Solid calcium carbonate reacts with HCl to form H2O, calcium chloride, and CO2. If a 45.0 gram sample of calcium carbonate is added to 1.25 liters of HCl aqueous, that is 25.7% HCl by mass, what will be the molarity of HCl in the solution after the reaction is completed? Assume that the solution volume remains constant. Yeah, so when we add solid, like 45 grams to 1.25 liters, you expect the volume to change a little bit. Right? So here we're going to assume the volume doesn't change. So we're going to have 1.25 liters. So all we have to figure out is how many moles of HCl. So this is just a stoichiometry problem. This is a stoichiometry problem with a little bit of a twist because we're given the percent by mass HCl that was in this solution. And so we can go from liters to milliliters, milliliters to grams of solution to grams of pure HCl, grams of pure HCl to grams, actually to moles of HCl. Yeah. The other stuff is extraneous, I think. 110, that was 110, 111. 111 is, well, this is another mixture problem. This is a 2.05 gram sample of iron aluminum alloy. Ferroaluminum is dissolved in excess HCl to produce 0.105 grams of hydrogen. What is the percent composition of mass of ferroaluminum? So each of these reactions is going to produce a different amount of hydrogen. And so we can see, you know, at the border, the hydrogen, we're 0.105 grams light, and then solve this graphically. So this is, look like a familiar problem. Okay. 112, a 0.15 gram sample, 155 gram. Actually, this would have been good to do. It's the same as 111. 113. Actually, maybe I should have given this earlier. In a dilute nitric acid solution, copper reacts to form copper nitrate. So nitric acid is an oxidizing acid. So this looks like single replacement, doesn't it?
Yeah.
But it's not single replacement because nitrate here is a more powerful oxidizer in the presence of H+. We have H+ present here. And so this is solved by the chart method. So if we solve this by the chart method, this is what we come up with. Now that's the complete equation from the chart method, but the chart method normally doesn't give us the complete equation. The chart method and the Bronsted acid-base method give us the net ionic equation. And so when we do this, if we're looking at single replacement and double replacement, both of these will give us the CE, and from the CE we'll get the IE, and from the IE we'll get the NIE. But when we use the chart method, either for Bronsted or redox, then we don't get the CE, IE, and NIE. We'll only get the NIE. If we want the CE, we have to work backwards. So for example, if we did the chart method to figure out what the products of this reaction are, you know, we would end up with copper 2, NO, and water. And then what we would have done is we would have worked backwards to figure out all the full formulas for the copper 2 nitrate and the HNO3. All right, so that would be a okay, excess reagent limiting reagent problem. Yeah. There's going to be a MESA session, you know, today, so you can ask her for I've skipped a lot of the basic calculations with stoichiometry and that type of stuff, but you can ask her for those if you need some refresher on that type of stuff. Okay, one last problem, 121. Silver nitrate is a very expensive chemical. Did I tell you what happened to our silver nitrate?
I think you touched on.
I touched on it.
Oh yeah, wasn't it
Touched on it
auctioned
yesterday?
off, and now you guys need it?
One,
I think you touched on me yesterday, but I think it poses a danger.
it's a danger. It's a danger, but you know, we used to have so much silver nitrate. So much silver nitrate. And then somebody came up with the idea that let's surplus it because we have too much silver nitrate.
Or we can make silver nitrate as a product for consumers.
Yeah, probably it's already used. I mean, I had a friend who was taking a lot of silver. His skin turned green. Have you heard of that?
Yes.
Oh man.
So he had this totally green complexion because he was taking some silver supplement. I don't know what it exactly was. But fortunately, it took about 10 years, but the green color had finally faded. But he did look like a Martian for a while.
Or the Incredible Hulk.
What's that?
Or the Incredible Hulk.
Yeah, or the Incredible Hulk, but he didn't have the physique for the opposite. Anyways, this, you know, when you work with these kind of things, it's like committee type stuff. And so I wanted to keep all the silver nitrate, but it was all surplus. In other words, it was all thrown away. But now we need silver nitrate and we can't afford to buy it anymore. It's crazy. And I think, wow, those are your tax dollars at work. Unfortunately, I'm sorry to pay tax for that and then have it all wasted. But anyway, you need 100.0 milliliters of 0.0750 molar silver nitrate, but only 60 milliliters of 0.0500 molar silver nitrate is available. You decide to pipette exactly 50 milliliters of solution to 100 milliliter fast and add appropriate mass of silver nitrate and then dilute the solution to 100 milliliters. What mass of silver nitrate do you use? This is kind of solution dilution plus a twist. The added twist is you got to add a little bit more silver nitrate, and then you assume that adding the solid silver nitrate is not going to change the volume at all, kind of thing. Or actually, you can add it before you dilute it, so it's not. So. All right, now chapter 5 deals with reactions, and I didn't follow this exactly as presented in the book, but we'll take a look at the homework problems that I assigned for this. All right, let's. For aqueous ammonia conducts electric current only weakly. The same is true for aqueous acetic acid. When these solutions are mixed, however, the resulting solution is a good conductor. How do you explain this? Well, here comes a, you know, aqueous ammonia is always a tricky thing to deal with in chemical reactions. And so there are a couple of ways I would deal with this. You know, if we mix ammonia, which is a base, with acetic acid, which is an acid, we're going to have a reaction, an acid-base reaction. There are a couple of ways of dealing with this. One way of dealing with this is ammonia. You can deal with this in terms of metathesis. In terms of metathesis, the way we deal with ammonia is we treat this as ammonia and water, which makes ammonium hydroxide. Ammonium ions and hydroxide ions. And then we treat the ammonium hydroxide as the AD part of this, AD. The other way of dealing with this is Bronsted. ammonia is a proton acceptor, so it can take a proton to form ammonium. Or ammonia is a proton donor, but it's really poor proton donor. Ammonia is not normally thought of as an acid. To make amide plus a proton or acid. And so if we have ammonia plus acetic acid, then if I do this Bronsted, what we do is we only transfer one proton at a time. So in Bronsted, the acid is a proton donor. And it's going to donate a proton to the base. And so what we're going to end up with is we're going to end up with ammonium ions and acetate ions. Acetate ions are going to be written like this, where it shows the formal charge on the oxygen at the end there. So we're going to have the charges like that. I don't have to circle it, I just circle it just to have this happen. All right, now we're going to have ions in solution. Here, is there a driving force for this? So we'll take a look and see if we have any driving force by looking at the redox chart, the acid-base chart here. And we're going to compare the two acids. What's the acid going forward?
Oh, acetic.
Acetic. So this is my acid going forward. What's the acid going reverse, if I were to go reverse here?
Acetate. Or ammonium.
Ammonium. And so I'm going to compare acetic acid versus ammonium and see which one is stronger. So acetic acid is here, CH3COH. And then where's ammonium? Scroll down here. Ammonium's here. And so we're going from a stronger acid, acetic acid, to weaker acid, ammonium. So that's what we have here. Stronger acid to weaker acid. And therefore we have driving force. Therefore what we're doing is we're going to form, the products are ions, and it's going to conduct electricity pretty well. Now if we do this using metathesis, then what we do is we'll put ammonia and water plus acetic acid. And so this is going to be a metathesis style reaction or double replacement reaction. The double replacement reaction is going to be like this. I'm going to rewrite this here. This one we're going to treat as ammonium hydroxide. I'll put it in quotation marks because ammonium hydroxide is not stable, it decomposes into ammonia and water. Although you'll notice that the bottle or the beaker, was it yesterday, said ammonium hydroxide. Did you notice that? It used to be thought of as ammonium hydroxide, but further studies, like all the old bottles of aqueous ammonia say ammonium hydroxide. And this one we'll get in BC, so I mean AB plus CD. We'll get it in CD fashion. So CD fashion is HC2H3O2. So this is my AB, and this is my CD. So I'm going to form ammonium acetate and water. And so this would be my metathesis reaction. And the thing here is this. What is the acid going in the forward direction? This. But what is the acid going in the reverse direction?
Sodium carbonic. Not sodium carbonic. Ammonia carbonic. There's carbonic.
Carbonic?
Is that carbonic?
No.
C2. No.
C2H3O2.
It's acetic.
Acetic. That would be, this would be ammonium acetate.
Ah. And
Yes.
the ammonium acid.
Yeah, there's, as far as there's carbonate, carbonate is CO3, 2 minus. And there's carbonic acid, which would be H2CO3. This is just straight, just straight memorization. Memorizing until. So what is the acid going in the reverse direction to get the driving force for this? Yeah. The acid in the reverse, it's a bit tricky, but the acid in the reverse direction is we have to look at what's losing the hydrogen. But it depends on what you're looking at, because if you're looking at hydroxide, then the conjugate acid of hydroxide is indeed water. But something weird happens here, and something that's weird happens is the waters cancel. And so there's no more water in here. And so what we're left with is an equation that looks like this up here. And the acid really is ammonium. That's our acid. And the base is going to be acetate. Acetate is going to be a proton acceptor, make acetic acid, and ammonium is going to be a proton donor, which makes ammonia going backwards. Yeah. And so water is very common. You know, and a lot of Chem 4 instructors say this. What's the driving force for the reaction? Formation of water. But in this case, no, formation of water wouldn't. In fact, a lot of people tell me that the formation of water is the driving force for this particular reaction, but the waters cancel. Yeah. So it doesn't quite work. So I just wanted to talk about that briefly. Okay, after number 4 comes number 5. Sketches A through C are molecular views of the solute in an aqueous solution. For each sketch, indicate whether the solute is strong, weak, or non-electrolyte. So A, strong, weak, or non-electrolyte? Strong. B, weak, I think.
It could be.
Oh, yeah, this is weak because look at this one. You see it's missing.
Yeah.
H. There, it's missing an H on one of those. This must be a hydronium. This one? This one is actually, looks like a non. Is that non? Well, let's see what these are. Which substance is sodium chloride? Well, it's got to be this one. Propionic acid. Propionic acid is going to have 3 carbons. 1, 2, 3. This has got to be propionic acid here.
Yeah.
Hypochlorous acid. Is there more?
It's only those 3. They just give
They
us.
just have extra.
Oh, they have extra. Okay. No. Ammonia. Yes. This is ammonia. What's that? Water?
Yeah.
Yeah.
I believe it is water.
Yeah. So that is, this has got to be aqueous ammonia. Aqueous ammonia, though, is a weak electrolyte.
Yeah. It is weak.
Yeah. So maybe I don't like this problem that much anymore. Bye. Yeah, propanoic acid. Some people will call it propionic acid, but most people will call it propanoic acid. Propanoic acid. But you'll have some, and then some people are very, they'll have a very strong stance on what it should be called. Like, and some people just won't care. Propionic acid or propanoic acid. PubChem has it. Oh, PubChem has a propionic acid. Propanoic acid. NIST has a propanoic acid. All right, then 10, 12, and 17 deal with some solution type problems here. So we'll take a quick look at those. A solution is 0.126 molar potassium chloride and 0.148 molar magnesium chloride. What are the potassium? Well, potassium is going to be 0.126. Magnesium is going to be 0.148, but chloride is going to be added these two together. So 0.126 plus 0.148, since they're in the same volume. If you're mixing them, then that changes things because there's a solution, but you're not mixing them here. 12, the molarity of sodium fluoride. What molarity of sodium fluoride corresponds to a fluoride ion content of 0.9 milligrams of fluoride per liter. The federal government's recommended limit for fluoride ion in drinking water. So you can convert that to molarity. Milligrams to grams, grams to moles, and then we're done with that problem. And so just some more solution problems. I'll skip 17 for right now. Let's take a look at 19 here. These are double replacement tile. These are metathesis. They don't fit the pattern, but these are close enough to the pattern, AB plus CD. All you're looking for is favorable ion combinations. So here, do you see any? I do. With two ions like each other. In A.
Sodium bro.
No.
Sodium and nitrate.
No.
Lead, 2, and bromide.
Yeah, we're going to precipitate lead 2 bromide. That's what we're looking for. We're looking for precipitates. Here, B, the two ions like each other.
None.
None.
Not,
Yeah.
not likely, none.
No reaction. C,
Sodium hydroxide.
Iron.
yeah, iron and hydroxide. Iron and hydroxide will precipitate right away. It's not that you can't make sodium hydroxide though, but you have to force sodium and hydroxide together. If you have aqueous sodium hydroxide, what you have to do is keep evaporating the water. And keep evaporating the water until there's no more water left, and then they're forced to come together. But you're going to have to wait until it's completely evaporated to make the sodium hydroxide. Otherwise, they're not going to come together. They're going to stay apart from each other. And so these are just getting practice with metathesis. 20A. Do you see ions that like each other?
Calcium carbonate.
Yeah, calcium carbonate will precipitate. B,
Barium sulfate.
barium sulfate. Sulfates are all soluble except for silver.
Lead,
Mercury.
mercury, calcium, strontium, barium.
Barium sulfate precipitates. In fact, we're going to do a barium sulfate precipitation in lab.
The next lab?
Not the next lab, but pretty soon. What we're going to do in that particular lab is we're going to do a quantitative determination of the percent sulfate in an unknown sample. C,
Potassium chloride.
no. Potassium chloride will stay away from each other until the water evaporates, forcing potassiums and chlorides together.
None.
Would
None.
None.
'21. Did anybody already do these?
I did it all.
You did all of them already?
Not all of them, like half.
Half of them, all right. These are just double replacement reactions, so we look for driving forces for that. Let me see. What time do we go till?
12:55.
55, all right, so
We
we're
got
almost,
like 6 minutes left.
yeah. And then we go on to some acid-base reactions here. Acid-base reactions. These ones, you could do double replacement, or you could do Bronsted. So let me, let's take a look at C here, for instance. Some of these you can't, like this one, is this an acid base? Why are they calling this acid base? E is not an acid base. What is E? Redox. And so E's definitely out of place there. E does not belong. If we have magnesium, which is a good reducing agent, and H plus, which is a good oxidizer, and water, which isn't good at either, oxidizing or reducing, we're gonna have a reaction. So this is actually a single replacement reaction, in which we're gonna take magnesium solid plus 2H plus. This is gonna form magnesium ion plus hydrogen gas. And the driving force here is we're going from stronger reducer to weaker reducer, or more active to less active. And so this is not acid-base, this is redox. But did you recognize this as a single replacement? You know, this is H plus from any mineral acid. You know, the anine's a spectator, X minus. If it's an oxidizing acid, it doesn't quite work. But one of these reactions I want to talk about here would be C. The reason is because we handle it in two different ways. When we do Bronsted, we only transfer one proton. So Bronsted is proton transfer from the acid to the base. And we always do it just one step at a time. But if we were to do metathesis, we do complete reaction. And so if I had something like this, FeS plus HI aqueous, HI is a strong acid. Strong acids are going to ionize completely. What I do is I do complete reaction. And so complete reaction, this would be iron 2 iodide. So I'm going to form iron 2 iodide. And what? And hydrogen sulfide. Hydrogen sulfide is H2S. So this is metathesis for double replacement. And what we do is we just do complete reaction. We don't do partial reaction. Because we could, I mean, it depends on how, if we have some prior knowledge of what's going on. Now, if I do this Bronsted, I do it differently. So Bronsted, we have FeS. Again, the sulfide's a pretty good base, but it's locked in the lattice. Normally sulfide is a strong, powerful base. But when it's locked in this crystal lattice here, it's not going to be nearly as powerful. And then we have H plus here. And so this could also be done Lewis, you know, Fe2 plus plus the sulfide. Sulfide's going to have a complete octet like this, and it's going to have a 2 minus charge. And so this is just going to pick up that proton. When that happens, we're going to make FeHS. Minus. So this would be partial reaction. The hydrogen sulfide is going to make this more soluble, so we're just going to end up creating the sulfide. Not creating, but neutralizing the sulfide to hydrogen sulfide. And so we do one step at a time. Now, if we have more H plus, what's going to happen is either stop here, or we react it with another H plus. Another H plus means this HS minus can tack another H plus, and then finally make an H2S. And so for Bronsted, we do it one step at a time. And for the Bronsted in this chapter, we're only going to do one step. Stop here for Chem 1A. For Chem 1B, we would do it step by step, and then we'd analyze each step along the way, and then do the stoichiometry for that. For double replacement, we're taking it all the way to H2S. For Bronsted, we're just neutralizing it one proton at a time. Okay. All right. Well, I was supposed to get into chapter 6 today, but I'll get into chapter 6.
Thursday.
Tomorrow or Thursday?
Tomorrow, yeah, or Thursday. I'll get into it Thursday. Question?